I didn't tell you you were being recorded. You were being recorded, just so you know. And Amanda's listening to you, I think.
Yes, I
Is
am.
Amanda still there?
I'm here and I am definitely
Okay.
listening.
Okay.
Hi, Amanda.
Hello.
Can you hear some of Byron's stuff? He's pretty far away.
Yeah, I can't hear him very well. I heard that hello, but I can't make out most of what he says.
He doesn't say anything worthwhile anyway.
Well, I heard that.
Byron, you need to speak up.
Yeah. He'd rather chirp and beat.
Okay. He's back there playing with his radio. I think he's going to try to do a demo.
Oh,
All
exciting.
right. Specialized antennas. One question on this group. An inverted V dipole, okay, which is a half-wave dipole where the center is elevated above the endpoints. If it's 45 degrees, you get about a 50 ohm feed point impedance as opposed to the normal 72. As you get it less and less than 45 degrees, the impedance starts going down. So they consider 45 degrees the optimum for an inverted dipole. And normally you would want the height of the center to be at least a half wavelength. Now the bottom ends, because it's going to be very high impedance on the end, you're going to have high voltages. You would normally want those endpoints to be at least 8 or 10 feet above the ground so people can't easily touch it, because then they'll get some of those RF burns we talked about if they happen to be grabbing it while you're transmitting.
Yeah, they can teach them that.
Yeah, they mess up.
One thing about it, you get that out straight, so it was at 7.3 megs, right? And then you bring it down, it now drops frequency. That's resonant at it.
Wonder what's affecting that. Changing capacitance?
Capacitance, because
Okay. Starting as you get them closer together, they're starting to
Yeah.
show some more capacitance.
and if you get them almost like
Yeah.
coming straight down, you get a very narrow frequency. It's like a fence antenna, or it's almost like a one
That happens when we get old.
I know I'm getting there, but you can get it where it's true, where it's only, I had one for like 80 meters. It was only good for like 25, maybe 50 kilohertz. Well, man, it was right on the resonance. That inside was way up.
Hey.
Like a magnetic loop. That's what it.
What is the common name of a dipole with a single central support? This is a hard one. Now you can't have inverted L's, where one part of it's horizontal and one part of it is straight up.
After this, it's gonna be a lazy age.
Okay. Another specialized is a log periodic, similar to the Yagi, but the formula for them is quite different, and the elements decrease logarithmically, and the spacing between them decreases logarithmically. They're wider bandwidth than a Yagi. They're lower gain than a Yagi. I'm not sure about the front to back ratio. I think it's probably similar. But the big thing is it's wider bandwidth, lower gain. You used to see those on TV antennas a lot were log periodics.
TV antennas for a while, still a lot throughout boards.
Yeah.
The thing is, they're all driven helmets.
Ah, okay.
Every one's a driven helmet, they cross and back and forth.
Oh, that's right.
Fully.
Yeah, that's right. I remember now. And looking at one, the TV one, and yeah, they did the phasing thing between each element.
When I was in Africa, they had one. And it was crossed in the middle, without like this, continuously back and forth. So it was been interpreted at the very end. Back around. I don't know why.
Okay. It also looks like this one in the picture's got a matching transformer here at the end. I'm assuming that's what that little box is. Okay, which of the following describes a log periodic antenna? Log periodic antenna.
What's an option? No.
Yeah. All these others are just red herrings. They throw periodically in or logarithmically in just to confuse you. But the element length and spacing varies logarithmically along the boom. And you always see them in sort of a triangular fashion because of that. Which of the following is an advantage of a log periodic antenna? Right, wider bandwidth. They should have said relative to a Yagi, but I guess it's wider bandwidth than most of the beam antennas.
Even the dipole,
Huh?
wider than the dipole.
Oh, it is?
Because it can cover multiple beams. And think about how wide the TV channels are spaced out.
That's true. I didn't know that.
From a blue broadcast band and
Right.
100 megahertz.
Yeah, so we went from what, 50 to 350, 400 megahertz on the broadcast TV band. I remember channel 2 was like 50. Back when they used to have over the air broadcasts. Okay. Near vertical incidence skywave or NVIS. Byron is our NVIS expert. A horizontal dipole placed 1/10 and 1/4 wavelength above the ground gives a very high angle of radiation, close to 90 degrees.
That can't make it too.
What?
Could probably make it too. 1/10. Okay, I'll like that.
Well, it says between 1/10.
Yeah.
Um,
Yeah.
And it uses ground reflections to help radiation pattern. The one they're showing in or the one I found to stick in there shows reflector wires on the ground. I guess if you had very good soil or you strung it up over the water, you'd get a very,
Where you live on an island with real close water.
yeah, put it on the beach because the ground reflections help. Here's some pictures in this first one. A, you probably can't read it, is 1/8 of a wavelength above the ground. B is a quarter wavelength. C is half wavelength, and see, we're back to our typical kind of two lobes. And then as we start going above half wavelength, then we start getting all these additional lobes. And the higher you go, the more of them you have. Now, the bottom lobe, which has slightly more power than the others, keeps getting a lower takeoff angle, but you're losing most of your power over in these other lobes. So you're not gaining a lot, which is why half wavelength is apparently the optimum height for a dipole. And a vertical. And a vertical. Well, and it's hard to do for the lower bands. 40 meters is pretty high for an 80. Well, yeah, but you don't need that if you're 160. So, which of the following antenna types will be most effective as a INVIS antenna for short skip communications on 40 meters during the day? Right. Okay, beverage antennas. It's a basically receive-only antenna used on the low HF bands. It's very, very lossy, which is why you don't transmit. And if you look at the configuration, you've got this 470 ohm resistor on terminating one end of it and feeding it with a 75 to 450 transformer. So you would lose an awful lot of power over here. Make that a big resistor. It tends to radiate along the length of the wire, so it's directional. I don't know any more about them. I've never used one. I've only read about them. Ernie, do you know anything about it?
Not at all.
Byron?
Dave, a little bit. It's not what we now do.
Okay.
He likes something 60 meters and things.
Okay. What's the primary use of a beverage antenna? Right. Receiving antenna, basically. Very directional and good for low bands, assuming you can stretch out 160 meters of wire. Next, we have multi-bands, and what they're showing here is a typical fan dipole. Looks like this one's got 5 bands, and you notice each one of those, because of the size of the coil, is longer. So this first one is probably an 80 meter, followed by a 40. It could be a 30, 20, 10, hard to say. But it allows you to work on multiple bands with a single antenna. And once you've got all of those individual wires tuned, which is a long process, and you go do it multiple times. You start with the long one, and then you do the next one, and the next one, and the next one, and then you go back and you do it over, and then you go back and you do it over until you get all of them within range SWR that you want, because they interact with one another.
The protein goes down.
Yeah. I lowered mine, and when I put it back up, I had to retune it. They can radiate on harmonics, so they can also receive harmonics, so they can pick up stuff you don't want. And that's why it says it's poor harmonic rejection. Which of the following is a disadvantage of multiband antennas? Yeah. Right. You got multiband trap antennas can also be horizontal, but in this case, we're talking about a vertical. And the one they're showing is a 10 meter, 12 meter, and 20 meter vertical. So this lower trap is tuned for 10 meters. And if you remember from the technician stuff, parallel resonant tank circuit, tune circuit at resonance has what? Very high impedance. So when you're operating at transmitting or receiving at 10 meters, which is 28 something megahertz, you have a really high impedance, so you don't see the rest of the antenna. It appears to be just this short length. Same thing happens when you go to 12 meters. If this little tank circuit's resonant at 12 meters, it basically blocks off the last part of the antenna. And then for lower frequencies, you're going to pass through both of them, so you'll see the entire length. So it looks like it's three different length antennas, depending on what frequency you're operating at. And they say it appears electrically shorter than it actually is on certain bands. So
I was a little bit confused about things because the trail actually just outside of the main region a little bit lower.
it should be pretty close because you want it to be, I mean, it's not going to cover the whole band, but you want it to be as high impedance as you can. So you want it at its resonant point at, I guess, the high end of the part of the band you're looking at. I assume it's going to be fairly narrow bandwidth because of it, and it would depend on the Q of that tuned circuit.
Inherently, the higher the frequency it go, transmitting lower that frequency will get quicker. If you go down lower, it's going to get higher in cadence. It's probably increased before that. So you can off.
What is the primary function of antenna traps? Multiband operation. And you do the same thing on a dipole. You can put traps on a dipole and make it appear as a multiband dipole.
We sell those on the.
Yeah.
They're short, they get shorter also.
Uh,
They put it in the document. Series.
you don't have to go through all the tuning stuff that you do on a fan dipole.
That's right.
An in-fed half wave. Byron's favorite. It's a half wave dipole that you feed at one end. Doesn't matter whether it's left or right. It's usually the end closer to the ground. It doesn't have to be. And it has very high feed point impedance. It's going to be several thousand ohms at least. They're very easy to carry around as a portable setup for doing QRP or stuff. And you find some way to toss one end of it up over a tree or something to get it elevated.
The downside is that
Speak up.
the downside is the transformer. It's sensitive to noise of a lot of home installations. You end up with the transformer away from the house.
Okay. And it does require a matching device, which is usually like a 49-to-1 impedance transformer. Which, let's see.
There's something to remind one. That train of wire.
Yeah, if you're going to go 50 to 5,000, you need 100 to 1. It's probably not 5,000, but so they tend to use 49 to 1, but I've also seen 64 to 1 and whatever the next one is up.
56.
You could have, 81 to 1, 9 turns.
Random link that's
Right. Random uses it because it's not as high an impedance.
right. Not as high.
But apparently 49 to 1 does a pretty good job. I mean, it's not a perfect match, but it's close enough.
Mm-hmm.
What is the feed point impedance of an end-fed half-wave antenna?
Wow.
Why?
Very.
Yeah. Why is it high? What do we know about an antenna? We've got current going through the wire, right? And well, remember Ohm's law. So at the very end of the wire, how much current is flowing? Essentially zero. Okay, and if I've got 100 watts on there, I've got a E over I. E is going to be pretty high. And if I, likewise, the impedance is going to be very high. They have a high voltage and essentially no current. Magnetic loops, they're, in most cases, I guess they're portable. Most of them are less than 3 or 4 feet in diameter. It says they're less than 1/3 wavelength in circumference. They're easy to set up. Usually when you buy them, they come with some sort of stand or tripod, so you can set it up indoors or outdoors. They have a very good null pattern. It's broadside to the loop, so you can kind of use it as a directional antenna, like for direction finding, except when you null it, you don't know whether it's this way or that way. They're extremely narrow bandwidth, and you have to tune it by the tuning capacitor, which is at the ends of this loop. So it's going to be operating at a very high voltage, which, like Ernie said, they're usually in the commercial ones, a vacuum capacitor with some motor to drive it so that you can tune it remotely. Because if you're running much power and you're right next to it tuning it, you're getting radiated way above the exposure limits, which is another thing that makes them more expensive if they're remotely tuned. This shows the radiation pattern. And the blue one is supposed to be the vertical pattern. So you've kind of got a donut around the wire, kind of in the shape of the loop itself. And that's your radiation pattern.
But they're very good for DX and Dennis. Same time.
In which direction or directions does an electrically small loop, less than 1/10 wavelength in circumference, have nulls in its radiation pattern? Yeah, remember it's a donut around the loop. Okay, so we have nothing in the center of the loop, which is broadside. Screwdrivers. Here you go. You didn't open it up yet.
Where's the target?
It's a vertical antenna with a remotely adjustable bottom loading coil. If you look at the picture example, at the very bottom of it, there's a few turns of the coil, and your feed point is between the bottom end of it and those turns. And then you've got the body, and inside of it is the upper inductor. And that, as the motor rotates, that screws that inductor up or down. And as it, let's say, the part of the inductor that's inside the tube is essentially shorted out. So you've got an auto transformer, and you've got the number of turns on the bottom, plus the number of turns that are exposed on the coil. So as you rotate it and bring more of the coil out, you get a different turns ratio plus a different amount of inductance, which makes the antenna appear longer. So you're going to get it tuned for a lower frequency. And it allows you to go, I don't know, firing? What's the range on that one?
This is going to be 40 to 77.
Wow, 40 to 40 meters to 70 centimeters. Okay.
This is the G9D top.
And how much do they run?
They're about 3.5.
Okay.
$2.50.
Oh, you know what? That's what my chart says, except I got a typo. That should see 75 meters. Well, your case is, what'd you say, 10 meters to,
So we said
oh,
40 meters.
40 meters to 70 centimeters. Yeah. I need to change that chart.
Well, no. Most are 80 to 10. Yeah, or 80. The H ones. This is special.
He's got a special one?
It's different. I don't know if it's special. It's just different. It's like, but I'm like, yeah, he's different.
Well, we know you're special, but
Sorry, I know it's different. I don't know it's special.
what's special about yours than a regular one?
It matches the tuning circuit on the gate seal,
Okay.
and it has a little bit shorter stinger on the top for radiating element,
Okay. Shorter whip.
and that allows us to do the 70 centimeters.
Okay. So I'm assuming the inductor is all the way inside the case when you're at 70 centimeters.
Oh, yeah.
So it looks like a quarter wave 70 centimeter whip when you're all the way down.
That target has when it goes 80 meter to 2 meter. Yeah, I can see that.
Okay. So it gets its name from the electric motor that rotates the coil, kind of like an electric screwdriver. So how does a screwdriver multiple antenna adjust its feed point impedance? Going to change the number of turns on the coil, basically. So we're changing the inductance. Halos. I've never actually seen one. It's a portable VHF, UHF horizontally polarized, omnidirectional, half-wave dipole antenna. So it's a half-wave dipole for VHF, UHF, and they just bent the elements around in that halo shape. It makes it have an omnidirectional radiation pattern in the plane of the halo. So it's kind of like the mag loop. It's a donut around it, except it's radiating horizontally.
Sometimes at the end, I mean, that's not steam.
Yeah, I guess those are capacitive hats, which I still don't understand how they work.
All right.
That's another thing for another day.
Now, think about it, looks like the list. That's right itself.
Yeah, I know. But like I said, I don't understand the physics yet.
Oh. I don't even, I never tried to. It's all fault, man.
Well, I have that problem. I like to understand how things work more than using them.
That's pretty. And I know there's staff that tells about the magic.
Yeah. In which direction is the maximum radiation from a portable VHF, UHF halo antenna? Omnidirectional in the plane of the halo. Coffee break, pee break.